Compartmental models in epidemiology. A compartmental model allows us to simulate the evolution of different groups in a population. For example, epidemiologists use compartmental models to track the evolution of infectious diseases. The basic idea is to divide the population into different categories or compartments depending on their stage of the disease. To illustrate, a model for the seasonal flu contains two compartments, one for susceptible individuals and the other for infected. At any given time, the model predicts the percentage of individuals in each compartment. This information is useful for researchers, policymakers, and healthcare providers. Why are these models important? Well, when COVID-19 changed our lives, I wanted to understand more about the transmission of disease, which led me to study compartmental models in depth because they can help you understand how diseases are retained within multiple populations. I started from the basics and further created more complex models. These models aid in determining the rate of transmission, the frequency of the population that can reach immunity, and the severity of the virus itself. Obviously, this depends on a variety of factors and is subject to interpretation. These models can also use real-world data to determine actions required on a provincial and national level in order to flatten the curve. I started studying one of the simplest models in epidemiology, the SIS model. In this model, the S compartment stands for the susceptible population and the I compartment stands for the infectious population. Scientists use the SIS model to predict the behavior of influenza and the common cold. In these diseases, the infectious population does not retain long-lasting immunity, and therefore, we observe a dual directionality, as the susceptible population goes to infectious and the infectious population goes back to susceptible. This model uses two parameters, the infection rate, which is denoted by beta, and the recovery rate, which is denoted by gamma. In this graph, you can see the susceptible and infected populations modeled as a function of time. The susceptible population starts off very high at 99%, and the infectious population starts off very low at 1%. As the susceptible population goes down, the infectious population goes up. This makes sense because those who are not susceptible will be classified as infected. The process continues until both the susceptible and the infectious population sterilize. The flat curve indicates that the infection rate equals the recovery rate. Unlike influenza, measles confers long-lasting immunity to recovered patients. To model this behavior, we use an SIR model. S represents the susceptible population, I represents the infected population, and R represents the recovered population. In essence, the susceptible population becomes infected, and the infected population recovers. The only path to immunity is by getting the disease, and therefore, the model is not suitable in situations where vaccination is an option. The parameters of this model remain the same with beta and gamma. In this graph, the susceptible population starts off very high at a rate of 99.9%. The infected and recovered populations start off at about 0%. The susceptible population declines until it reaches a constant flat curve. The infected population increases and then decreases and reaches a flat curve. The recovered population shows the greatest amount of increase and then flattens out. The general trend is that as the susceptible individuals go down, the infected and recovered individuals go up. In order to make this more realistic, the simulation incorporates some noise. After understanding a few basic compartmental models, I decided to code some of my own. This gave me the opportunity to study the evolution of diseases under various circumstances. The more compartments the model undertakes, the more complex the model, and as such, the SUDRP model actually has 5 different compartments, where S stands for the susceptible population, U are those that are infected but undetected, D are those that are infected and detected, P are those that are deceased or passed, and R are those that are recovered. The idea is that an infected person may or may not detect the infection depending on the intensity of the symptoms and the available testing. Infected individuals can either recover or pass away. We assume that if a person passes away, the infection was previously detected. Some added parameters in this model consist of sigma, which is the rate of detection, gamma prime, which is the rate of recovery for the detected population, and gamma double prime, which is the rate of deaths. In this graph, the undetected, detected, recovered, and past populations start at a rate between 0 and 10%, whereas the susceptible population starts off very high at about 90%. Eventually, the rate of susceptibility and the infection rate are the same, after which the recovered individuals surpass the susceptible individuals. The infected, detected, and undetected individuals display a decrease, presumably because they move towards recovery or death, and the rate of death increases from 0% to a maximum of 15%, after which it reaches a constant rate. My final customized model is the SUD-RPV model, where I attempted to model COVID-19. This model contains an added vaccinated compartment to the SUD-RP model, totaling to 6 compartments. Here, the susceptible population is able to get vaccinated and can then move towards recovery. The added parameters are epsilon for the rate of vaccination and delta for the rate of return to susceptible. It is important to note that the model does not account for the 6-month immunity period or the new mutations of the virus, in which case it is unsure how effective the vaccine would be. In this graph, we exclude the rate of susceptibility since the change is minute. We can observe that the vaccinated and the recovered individuals seem to increase, all while the undetected and the detected individuals will decrease after a certain period of time. The past population displays only a minimal increase, and the added vaccination compartment can account for these changes as more individuals will work towards recovery. Moving on from my discussion of customizable models, what are some of the key takeaways that you can remember from this project? Well, compartmental models display trends in infectious diseases. These models are also key to epidemiological modeling and determining how we can reach herd immunity. Another important point to remember is that compartmental models can vary greatly and get increasingly complex as you add more compartments. This concludes my discussion on compartmental models. I hope you found this video informative and use it as an opportunity to come up with some of your own compartmental models in order to apply them to real-world situations. Thank you for watching.